Well, thank you for coming. My name is Max Fagin. I'm an aerospace engineer at Made in Space, a company based at the NASA Ames Research Center. We built and operate the 3D printers that are currently on the International Space Station. My background is in Mars entry, descent, and landing, but I currently do work mainly in Mars resources. And this is a project that I've been doing some research on for the last almost 10 years now. And it has to do with the various advantages of setting up space elevators in the solar system and why I think Mars is arguably the first place where a space elevator is going to become feasible. So a little bit of background on just what space elevators are and how they work. The first space elevator was proposed almost 5 decades ago. And the way they work is they are a tether which is lowered down from synchronous orbital altitude. So on Earth, that's about 40,000 kilometers above the surface. And by extending a tether downward and a corresponding tether upward, and always keeping the center of gravity over the geosync point, you can actually get a continuous structure reaching from the surface of the Earth up to space. Then by electrically hauling an object, the same way a conventional elevator does, up the tether, using electrical motors and solar panels, you can reach any altitude on the tether. And then when you let go, the centrifugal force throws you prograde off to various destinations, be that Mars, the asteroids, outer planets, anywhere in the solar system you need to go, provided the tether is long enough. Now, it's very important to understand this is not a tower. The structure is not a compressive structure that you build from the bottom up. It is a tether that is lowered down from orbit. It's very important to understand for how one of these things works. And the key reason why we would ever want to do something like this is no matter how you do it, you've got to get about 55 megajoules of energy into a kilogram here on Earth in order to get it away from the planet, no matter how you do it. And a rocket, the conventional way of doing it, is very inefficient. But if you do it with a space elevator, it can be as efficient as the electronics and motors that are lifting your elevator, which can be very efficient, 30 to 60% efficient. Contrast that with a rocket, which is propelled by an explosion, and it's less than 0.1% efficient. So this is enormous savings. We don't do this now because we don't have the technology to build a space elevator yet, but I would argue that that is going to change, and when it does change, Mars is going to be one of the first places where we'll want to build one of these things. So the history of this idea, like I said, started about 5 decades ago in practice, but the original idea was actually proposed in the 1800s, by Konstantin Tsiolkovsky of the Tsiolkovsky equation fame. He didn't have much technical details to it. The technical details were hashed out in the 60s. By Yuri Ostronov. Finally, in the late 1900s, we first had the materials developed that could actually support something like this. The key to making this work is extremely strong and very light materials, which we didn't have back in the early 1900s, but which we first developed with carbon nanotubes in the 70s and 80s. Today, we are to the point where we're manufacturing carbon nanotubes that we could use to make this work, but we are nowhere near the degree where we can manufacture enough of them to make a structure this big. In fact, we have no idea when we will be able to manufacture a structure this big. If you talk to CNT and space elevator experts, it's very much like fusion. Some of them will say we're 10 years away, others will say we're 100 years away. This a general range that I find the estimates lay in is no later than 2065, but absolutely nobody knows. If anyone tells you definitively when a space elevator is going to happen, then they're making it up. So the basic concept is, as I said, a tether that is extended from a synchronous orbital altitude, so that's geosync for Earth, aerosync for Mars, always keeping its center of gravity over the synchronous altitude. And by hauling the elements up the tether and then releasing them, you can get wherever you need to go. Now, if you run through the math of how this is supposed to work, you find that the tether can't be a uniform thickness. The tether has to be a discontinuous thickness given by what we call a taper function, which I've shown right here. The key takeaway, however, is that it has to bulge in the center. It has to bulge at the synchronous orbital altitude and then get thinner at the apex and at the base of the tether. And that goes according to this equation. Now, the key metric which determines when this becomes feasible or not is what we call the taper ratio. And the taper ratio is what you get if you divide the ratio of the maximum area, that's the area at synchronous altitude, by the area at the surface. This is the key design parameter that determines what makes a space elevator feasible or a complete dream. So if we look at what the taper ratio is determined by various materials of various strengths, we actually get an idea of the feasibility of this. In theory, you can build a space elevator out of absolutely any material. It just requires a completely insane taper ratio. If you were to try and make it out of steel, for example, you'd have to have a taper ratio of 10 to the 200th power. So 50 orders of magnitude wider than the universe is. So plainly, it's impossible with steel. If you move to something like Kevlar, it gets a little more realistic. It's still several billion times, it's still several million times worth of the taper ratio. We'd never build it, but at least it's not as wide as the planet. If we were to get to carbon nanotubes, the taper ratios finally get feasible. And this is one of the reasons why most space elevator advocates are convinced that we're not going to see a space elevator until you get carbon nanotubes. However, these are for a terrestrial space elevator. If we go back to that equation which I showed you, you'll notice that many of the key parameters that determine what a space elevator can do depend on the properties of the planet. And they are extremely sensitive to what planet you assume. For example, the taper ratio of the planet goes as an exponential of the planet's radius and as an exponential to a third power of the planet mass. Mars is considerably less massive than Earth, and it is considerably smaller. These factors combine to mean that if you had a carbon nanotube of a given strength, it would be about 250 times easier to manufacture a space elevator out of these carbon nanotubes on Mars than it would on Earth. So everything is stacked in favor of doing something like this on Mars than on Earth. This is a plot showing the amount of carbon nanotubes we'd have to manufacture and the taper ratio versus what specific strength we are assuming for the carbon nanotubes. This is currently what we're able to accomplish in the lab, about 7 megapascals per kilogram meter cube, which is something we actually call the mega-Yuri after Yuri Arsenov. And you can see here on Earth, we'd require over 1 million tons of carbon nanotube. We'd never make that. On Earth, it's still an insanely large amount. We still have to make 4,000 tons of carbon nanotubes, but that's at least something we might consider doing. And if we are going to allow carbon nanotubes to get stronger in the future, the theoretical limit is about 100 mega-Yuri. But most carbon nanotube experts admit that a realistic number is more like 38 mega-Yuri. The project is still enormously more feasible on Mars than it is on Earth. Now, why would we build something like this on Mars versus on Earth? Well, if we are operating under the assumption that Mars is going to be an export hub to places like the asteroids, providing mass-intensive stuff that the asteroids can't get, or places in the outer solar system, like the moons of Jupiter or Saturn, if we assume that Mars is going to be a mass exporter of these, a space elevator is a way to knock more than 70% of the delta V off of this trip, because most of the energy comes from centrifugal force of the elevator slinging you around and letting go, which you get from motors and solar panels. So the result of this is it's a drastic reduction in the delta V requirements to transport from Mars to pretty much anywhere in the solar system. You can see you can get from Mars to the asteroids for a little more than 1 kilometer per second if you're talking about the near asteroid belt. And that is, again, this is from the surface of Mars. This is not from a Mars escape or from Mars geosync, or Mars aerosync. This is from the surface of Mars. This is the amount of delta V required to get various places if you just climb up the tether and then let go. So it is an enabler of an export economy for the planet Mars. Now on Earth, let's take a look, let's get some actual numbers to how much easier it would be. Using these various assumptions, which are kind of standard assumptions that the Association for Space Elevator Studies makes, the International Space Elevator Consortium makes, assuming we are going to be manufacturing the space elevator, the carbon nanotubes from something like a C-type carbon-rich asteroid, with something like 80% yield and a total 3% carbon content, and present-day carbon nanotube strength, so no advancements, present-day strength, we could get it done in about 3.5 decades, 35 years using about 4,000 tons of material. That's a big project. That's bigger than the Large Hadron Collider. But it's way, way more feasible than trying to do something on Earth. We don't have 210,000 years to do something like this. But if we assume that there's going to be a continued advancement in carbon nanotubes, you can see it is going to be feasible on Mars long before it is feasible on Earth. There are even more advantages to doing this on Mars than there are to doing it on Earth. Earth has to contend with an atmosphere. Most of the major mechanical considerations for designing a tether have to do with how do I design it to survive wind shear in the upper atmosphere, and how do we design it to survive how do we design it to survive hurricanes? How do we design it to survive lightning strikes? How do we design it to survive atomic oxygen degradation from the parts that are in the ionosphere? And also, somewhat importantly, how do we design it to accommodate for the people who absolutely will not have this thing standing near them because, oh God, what happens when it falls down? Mars has none of these problems. Mars has absolutely has a negligible atmosphere, and more importantly, it has the third tallest mountain on its surface, Pavonis Mons, is right on the equator, right where we need this thing. So Mars is pretty much the perfect place to build a space elevator like this. You can design the entire system, the climbers, the tethers, optimized for just one environment, the environment of space. So what are the downsides of this? Why wouldn't we do this? Well, there's the obvious question of power. There is less irradiance available at Mars because it's farther from the sun, about 50% reduction in power, but conveniently, Mars is smaller. Mars has about a 57% reduction in irradiance, but a 62% reduction in gravity. So if you took a terrestrial space elevator climber and put it on Mars, it would be 14% more efficient. Now, the big reason why we might not do this, let's talk about Phobos. This is a true scale size Phobos to all of Los Angeles. So here's LAX, here's the peninsula of Los Angeles, here's the valley, and here we are up in Pasadena. This is the size of Phobos. It's about 22 kilometers across on its largest axis, and it is right smack where we want to put this space elevator. The space elevator, by design, must be on the equator, and Phobos is about a 1 degree inclination away from the equator, and it orbits below the aerosynchronous orbit altitude. So every 7 hours, it's going to come screaming by the tether. And approximately every 4 sols, we're going to get a close pass. That's one where it might conceivably collide with the elevator if it's in the right orientation. And every 14 sols, we are guaranteed a collision. So how do we solve this problem? The solution, which we call the twang, borrowing from space shuttle nomenclature, but which we are also calling the Clarke oscillation, because actually the original proposal for this was not in any technical literature. It was in Arthur C. Clarke's 1976 book, The Fountains of Paradise. And it has to do with the fact that when a climber climbs the space elevator, there are Coriolis forces that act on it that are going to try to force it to the west. And when that happens, you get a little bulge in the tether. And that tether propagates up above the climber. If you time things exactly right, just as Phobos is coming along, you launch a climber at exactly the right moment, the twang traverses along the space elevator, the whole thing dodges its hip right out of the way, and you miss Phobos by almost 2 kilometers. So does this sound crazy? Maybe. It certainly might look scary. Trying to visualize this data here. So this is looking down at Pavonis Mons. The green cross is where the base station would be. This is about 60 sols worth of passes with Phobos. Many of them are pretty far away. This is true scale Phobos size. Many of them are pretty far away, but some of them are right through where the space elevator needs to be. Pretty damn close.
2 kilometers past the radius?
Yep. 2 kilometers past the radius. Here's another way to kind of visualize it. So this is the altitude of the tether that Phobos makes its pass. This is the center of Phobos, the closest pass distance. So these are various close passes. It touches the yellow zone here. That's a possible collision. If it touches the red zone, that's a definite collision, unless you get the tether out of the way. Now, the tether is only about the cross-sectional area of your arm, but it's over 60,000 kilometers long. There is no way to make that a rigid structure. These oscillations are inevitable. Most of the time, the tether is going to dodge Phobos just fine without scheduling traffic. But by scheduling traffic, you can precisely tune the elevator so that this isn't a problem. And if this sounds scary, I understand why. But imagine trying to tell someone in the 1900s that we are going to have 2,000 aircraft flying in our airspace and having no mid-air collisions, no en route collisions for over 2 decades. And this system is considerably simpler from a physics perspective. We can predict Phobos and the tether's position to millisecond and sub-meter precision if desired. This is simple Newtonian physics. So while this might sound alarming, I promise you it is a problem that we can calculate. It is a problem that we can solve. It's not a showstopper. It's not a reason not to do this on Mars. But what if? Just because it's sometimes kind of fun to watch things go wrong, what would it look like if it fell down? This is pure disaster porn, absolutely nothing involved with it. This is a simulation that I put together of what would happen should the tether be severed at its absolute worst point. That's at the counterweight up here that's labeled Clarke. So here's Phobos coming around. What if the tether did break? This is not a Phobos-induced collision. This is say a terrorist-induced collision or an incompetence-induced collision, something like that. And you can see the time scale down here on the left. So this is half of a sol has passed so far. The tether whips around. It actually cracks twice. And over the course of less than a single sol, it rips around the planet 2 times and a little more to spare. So that's pure disaster porn. No, do not pay no attention to this if you're a policymaker. Just pay attention to it if you like watching big things go boom. So in summary, the space elevator is something we've been studying for a really long time. We know how it works in theory. Everybody is watching the carbon nanotube industry like a hawk, trying to figure out when they are going to reach the required point. And no one knows. There is no Moore's law for carbon nanotubes, unfortunately. It would be great if carbon nanotubes were like the silicon industry in the 1950s, where we are about to take off on an exponential curve and everything is about to get a lot easier. But unfortunately, it just doesn't seem to be that way. We've been manufacturing carbon nanotubes since the 80s, and there's been no exponential takeoff. They have gotten stronger, but it's a very slow, linear process. And we still have no idea if it's even physically possible to manufacture carbon nanotubes of the strength required to make a terrestrial space elevator. But we do know, because we've already reached this point, that it is possible to make carbon nanotubes strong enough for a Martian space elevator. So it just becomes a race. Is Mars going to need to support an export economy before carbon nanotubes reach the point where it is going to be practical to build one on Earth? And I would argue, based on the talks you're going to be seeing here and based on the plans for Mars colonization, that the former is more likely to occur than the latter. We are more likely to see a market develop on Mars that is going to need to export massive amounts of payload to the asteroids, to Earth, to Jupiter, before we are likely to see carbon nanotubes develop to the point where they can manufacture a terrestrial scale of carbon nanotubes. So given that, I really do think that if we had to bet on when the space elevator was going to first show up, probably going to be Mars would be my bet for when it is. When, I can't tell you, but I do think that it will be before Earth happens. Thank you. Yes? There is, yes. By having the majority of the mass present in the tether, not the climbers. The climbers are a small portion of the total mass that is climbing up the tether. But you're absolutely right. The whole tether does shake like a spring when you let go because you've suddenly unloaded it. Dr. Zubin. Oh, sorry.
I'm wondering, what about a lunar space elevator? Why wouldn't that be a lot easier? It's only 16% Earth's gravity instead of 33% or whatever.
So if your only question is, what is the most physically plausible place to build a space elevator, it's the moon. But
Right.
The advantages of a space elevator over a rocket are that you get to use electromechanical propulsion to launch something from a surface. The moon doesn't need a space elevator to launch things electromechanically from the surface. It doesn't have an atmosphere. You can use a railgun. You can use a purely electromechanical system that's based entirely on the surface to affect the same delta V without the need for a space elevator. You can't do that on Earth or on Mars because it would mean moving at hypersonic velocities through a very thick atmosphere. So if you just want to say, I want to see a space elevator as soon as possible, minimum feasibility criteria, you're absolutely right. The moon would be a much easier place to do it. We could do the moon with Kevlar if we wanted to. But if you're asking when would be the most economical place to do it, when will the forces of economy and physics and industry and capital align excuse me, to make a space elevator feasible, I would argue it means Mars because the moon has the electromechanical catapult option. Dr. Zoomer?
Back in the 90s, I wrote a paper called Hypersonic Skyhook, where you put the center of gravity of the skyhook in an orbit, like maybe a medium Earth orbit, where you're moving around the Earth at 4 kilometers a second or so, and then you hang the tether down from there, and because it's going to a smaller radius, it's maybe moving with respect to the surface of the Earth at 1 kilometer a second or something, and then you do a suborbital thing and you do a rendezvous with the bottom of the tether and then just climb up it, and this greatly reduces the length, mass, and taper ratio and all those things of it. Now, I'm wondering about Phobos as using it for such a purpose. That is, if you were to hang a tether down from Phobos, it would be moving with respect to the ground at less than 1 kilometer a second. And so with a very tiny delta V, you could do a suborbital climb to it and then you climb the tether out from it, and you're going interplanetary or wherever you like. Have you looked at the masses required for a system like that?
I have not. However, while that would be an excellent way to get to Phobos from the surface, it would not be stable long-term as a way to get beyond, to a higher orbit than Phobos. If you were to pay a tether up beyond Phobos, because Phobos is not in a synchronous orbit, it's not going to stay pointing straight up. It's eventually going to start lagging behind.
Why wouldn't it keep going straight out? It has a negative gravity pull, a centrifugal force, if you will, that's holding it out.
Because the whole thing is not in, because the center of mass of the entire structure is not in a synchronous orbit. Maybe I'm misunderstanding what you're saying, but either way, I see no reason why that would not be something that we could do. It certainly sounds feasible as a way to launch to Phobos. While we were getting the next question queued up, I didn't know if I'd have time for this. I have a video rendering of what Phobos would look like. 5 minutes? Okay, cool, we've got time then. So this is a rendering of what Phobos would look like, what it would look like to watch Phobos fly by the space elevator if you were sitting on a car about 30 kilometers above where the center of mass of Phobos was going to be. So here we are in orbit around Mars. Coming in from the left, here's Phobos. This is not sped up. This is true time. This is approximately the speed that Phobos would be passing, that Phobos would be approaching the tether when viewed from our altitude. So again, Phobos is about 22 kilometers at its maximum extent, about 18 at its minimum, and 10 to the 18 tons of rock heading towards you. And then there's Mars in the background. This is with the twang. This is a miss. This is a miss. This is a safe pass. Yeah, it would. Yes, of course. So you could still see Pavonis, so it would be a pass. Sorry.
Could Phobos be used as a source of materials for the tether?
It could, but you would have to transport the materials up to aerosync. It's not entirely clear if the energy makes that an advantageous decision when the alternative is find a 30-meter asteroid somewhere in Mars's vicinity and then just break it into aerosynchronous orbit. You're right, it could. It's just not clear if the energy math makes it an advantageous thing to do.
Did you ever think about moving Phobos?
Yeah, I thought a lot about it. But if you've got that much energy to spare, just terraform the whole planet.
Yeah, but really, wouldn't it just, if you did it small amount over time?
You have 100,000 years to wait? It's
Well-
10 to the 18 tons. If you have that much energy available,
But you
there are
have to
much
move
more
it
profitable
much.
ways to spend it.
Three months ago, while the International Space Development Conference was being held near LAX, China announced 2045 for their working space elevator. Any comments?
So it depends on what you define as working. Working as in it can haul a CubeSat up from Earth orbit to geosync and then let it go, and it can do that once before it needs to be replaced? Possibly. There's a very big difference between a tether that only needs to support itself, it just needs to support itself and a tiny little mass, and a tether that can support enough mass and enough throughput to continually repair itself. Those are two very different concepts. Personally, I'd be skeptical of any claims with a definitive date as soon as that. But without knowing what they mean by a functional space elevator, it's impossible to say. Because you can see the trend is an exponential. So just a tiny little difference in your assumptions can make a huge difference in the outcome.
Hi, Max. This is Kay. How are you?
I'm doing well.
Good. Just had a really quick question on the mechanics of this, the actual elevator that's going up this arms-thick carbon nanotube rope, if you will.
Mm-hmm.
So at a certain point, it is susceptible to the gravity of Mars as it's climbing. What sort of, just out of curiosity, what sort of mechanic is it on rollers or something? How is it actually physically climbing this rope?
So I said it
Just
has the
curious.
cross-sectional area of your arm, but it doesn't have the shape of your arm. What it's more likely is it's probably a few hundred microns thick, spread out to maybe a meter wide and then bent into a C shape. That makes it a little more immune to micrometeorite impacts. It means a single meteorite can't come across and cut the entire thing. So picture kind of a bent tube about a meter across which as the tether climbs using wheels, it just flexes into a flat shape and then reflexes back to a C shape. Pretty much. Yeah, it could be done electromechanically, but we've already got enough roadblocks in our way. There's no reason to assume. It is. Yep, it climbs up to geosync. After that point, you don't even need to climb anymore. You just relax the wheels and you will fall beyond that.
They've often defined the tether as as a lacy ribbon to make it so that a single a single piece of dust is going to take it out or tear it very badly. And if it's a ribbon, you conceivably could have the climbing wheel reach in between the tether gaps if it's well, so that you get a kind of a geared system that climbs it up. I wanted to say a little bit more about Phobos, and if you Olympus Pavonis Mons could feed the bottom of the Phobos tether to where it matches a maglev up the ramp or the side, could easily reach it's close to 12,000 miles an hour or something, but could easily reach the bottom of that. But now you said that it's going to precession because it's not quite at synchronous orbit?
If it weren't so Phobos orbits within a degree of the equatorial plane. So the only places that a tether lowered from Phobos would be accessible is on the equator, unless you set up a kind of north-south oscillation. Does that answer your question?
Oh, if you're doing a north, so it has to do a north-south oscillation if it's doing it.
If you want to access anywhere that's not on the equator.
East-west oscillation, you could also make it so that it's traveling at almost zero reference to the surface.
Yes, you could. It'd be a transient phenomenon, but yes, you could do that. Okay. Cool. Thank you.